was only 47. Now let's come to the present. Witten is 56. Polchinski is 53. Linday, one of the dominators of cosmology, is 60. Me, I happen to be 68.
Hans Peter?
Hans Peter's dead.
He continued until he was 90.
Yeah. Juan Malvicena, believe it or not, is 40. Alan Guth is 60. I don't know how old Lincoln is. This sounds wonderful, doesn't it? I mean, that people are going on so long. Well, I'm afraid it may mean something very bad. What I'm afraid is happening, and it troubles me, is, as we all know, science by its very nature is revolution and rebellion. I don't see it happening. I think it's time, young people, that you push us off the stage.
I tried to the other night.
But you failed. That, in my opinion, is the true trouble with physics. But it'll happen. Nature will take care of it. All right. I want to talk about eternal life. Eternal inflation. And one of the ways of thinking about it. All right, so I'm used to talking in this subject or to an audience of cosmologists or people who have been interested in cosmology for a while, and they all recognize this picture instantly. Does everybody recognize it? Does anybody not recognize it? Oh dear. Okay, so this is a picture of what happens in an eternally inflating universe. I'll tell you very quickly what it means. The purple region here is de Sitter space. If I draw de Sitter space as a conformal diagram, then it has a space-like boundary. The space-like boundary is time equals infinity. That's the conformal structure of the theory. The lower part is de Sitter space. If bubbles nucleate in de Sitter space, if de Sitter space is metastable, which many of us think it ought to be, if de Sitter space is metastable, if there are lower energy vacuums, and in string theory we know there are lower energy vacuums, both flat supersymmetric vacuums and anti-de Sitter vacuums, then bubbles can nucleate. This represents the nucleation of a bubble. Bubble wall goes out with the speed of light for all practical purposes. And I have drawn here basically a picture which would correspond to the nucleation of a bubble with exactly zero cosmological constant. If it didn't have exactly zero, why is it zero cosmological constant? Well, if you're familiar with drawing conformal diagrams for spaces, you know that flat space has a future infinity which looks like this. And what I've basically done here is cut out a piece of de Sitter space and patched in a piece of flat space. And that's the kind of thing that you see when you have bubble nucleation to a flat space. By flat space, I merely mean that the asymptotic vacuum energy goes to zero. I don't necessarily mean that it's exactly flat space, but asymptotically late time that the cosmological vacuum, the cosmological constant goes to zero. If the cosmological constant didn't go to zero, as in our own space-time, I'll come back to that later if I have a chance, then this would be rounded out a little bit. But in fact, if you actually drew it for our own space-time, because our cosmological constant is so small, it would almost look exactly like this with, you would need, well, I would say probably the roundedness over here on this screen would probably involve a deviation, something like about 1 Planck unit of height here. So it is not very, it doesn't change it very much. So I'm going to pretend that the world has absolutely zero cosmological constant. We'll come back to the implications of a real cosmological constant later. In string theory, and I suspect in any theory, the only vacuums with absolutely zero cosmological constant are probably supersymmetric. So if we really had to try to do this, we would be stuck with supersymmetric vacuums. And so be it. Let's study the cosmology of the nucleation of a world with zero cosmological constant. That's the exploration that I want to do today. How do we describe, how do we mathematically describe, how do we put together all the elements that we've learned over the last 10 years and so forth, some from string theory, some from the holographic principle, some from black hole ideas. How do we describe the world inside this nucleated bubble? Let's see, what button do I push to go to the next one? This one? Oh, yeah, that was good. Let me go back, though, first. What's this horizontal line, and why do I draw it? Well, the usual way of thinking about space-time is to foliate it with space-like surfaces and imagine quantum states on the first space-like surfaces, and then push them forward with some kind of Hamiltonian. This is a very dangerous thing to do in space-times. Not so much a dangerous thing. If one is going to do it, one has to do it with great care in order not to overcount if the space-time has horizons. And de Sitter space, in particular, there's all kinds of horizons in this space here. An observer looking from here, or an observer down here somewheres, cannot see out beyond this light cone here. And so there are all kinds of horizons there. And the reason I bring that up is because a lot of the questions which have to do with this kind of eternal inflation, this is eternal inflation, in between these interstitial spaces in here, between these bubbles, the vacuum continues to be de Sitter. There's more and more volume in them and more room for more and more bubbles to nucleate. I forgot what I was going to say. Let's just go on. Yeah. Oh, yes. The point is that one of the chief problems that people who think about eternal inflation this way come up against is the counting of vacuums. It's called the measure problem. How do you count? How do you put statistics on this? And if you're going to do it right, you better be very, very careful about overcounting and counting correctly the number of degrees of freedom, the number of possibilities, and so forth. And that can get problematic, particularly in the context of horizons. And I illustrated for you from a very well-known example, the example of a black hole. One of the things we found from starting with Bekenstein, going to Hawking, learning all about the information problem in black holes and so forth, is that we should not think of the degrees of freedom behind the horizon and in front of the horizon as being independent of each other. They're complementary descriptions of the same thing, in the sense that the Hawking radiation, which is carried off by the particles of the evaporation products, carry exactly the same information as the information that we would normally think is behind the horizon. Any other counting would overcount and would lead to this disastrous conclusion that information is lost behind the horizon. So this is something we have learned from black holes. And it has taught us not to try to think simultaneously behind the horizon and in front of the horizon. I don't know precisely what the lesson is for cosmology, but I would suggest the safest thing to do, which probably is closest in spirit to thinking about the black hole from outside the horizon consistently, would be to take the causal patch of the top of this diagram here. The top of the diagram is time like infinity. The causal patch of such a diagram, and a causal patch now means simply the backward light cone. For the black hole, the causal patch of future infinity would be the backward light cone of the point up at the top here. To take the backward light cone, which is all the points which can be seen by a late-time observer here, and restrict attention to them. So that is exactly what I'm going to do. I'm going to study basically the physics within one patch like this. What does an observer in there see? Now, of course, an observer in there pretty much constitutes all of ordinary cosmology, starting from the bubble nucleation. All right. One of the other things we've learned over the last decade or so, a little more than the last decade, is the holographic principle. In particular, we learned it most strongly in the context of anti-de Sitter space. I will come back to anti-de Sitter space. But basically what it says, again, it's a counting problem. It's very closely related to the counting problems of horizons, is that if we have a volume of space filled with a universe, ordinarily we would expect the number of possibilities, the number of degrees of freedom, the number of orthogonal states, and so forth, to be proportional to the volume of the space. And one of the things we've learned is that that cannot be true, simply because most of those possibilities would correspond to a black hole bigger than the region we're studying. And we've learned that the number of orthogonal degrees of freedom, the number of orthogonal states of a system, is proportional to the exponential of the area, not the volume. That's, of course, the holographic principle. And that holographic principle, in the context of anti-de Sitter space, has led to the idea of a duality between field theory on a boundary and bulk physics. And I want you to just keep that in mind as we go along. That should be, we should take that into account with any kind of consistent, precise description of our world. Now, let me come to the question of why we have had so much trouble using, in particular, string theory, but I think more generally than that, why we've had such trouble trying to think about cosmology. And I would say there really is no string theoretic framework at present that describes any interesting cosmological background. I think it's quite closely related to the questions that Leov asked about background independence and so forth. This is just another way of saying the same thing, but let me spell it out. String theory, and I suspect more than just string theory, can be very effective in describing a class of backgrounds which I call asymptotically cold. Asymptotically cold means all of the matter is localized, is a finite amount of it. It's localized in some finite region of space. And as you move away, you come to some very frozen, extremely definite background which doesn't fluctuate very much. In fact, which doesn't fluctuate at all. Example would be flat space. Of course, you're allowed to throw in a handful of particles. You're allowed to throw in a handful of particles from infinity, a small number. A small number means a finite number, and then you can talk about an S matrix, but you don't want to fill up the space with particles, because then you don't have sensible from the point of view of an S matrix, a sensible background. The same thing is true of anti-de Sitter space. It's also asymptotically cold or asymptotically frozen, and the reason is that it just takes an ever-increasing infinite amount of energy to bring a particle to the boundary. So if you put in a certain amount of matter, a certain finite amount of energy, it will tend to drift to the center, the boundaries being completely frozen. Okay? That's exactly what's not true for any interesting cosmology. First of all, for closed cosmologies, there are no asymptotic boundaries, period. For open cosmologies, which I will be interested in, particular open FRW, open means negatively curved, FRW, k equals -1, or for that matter, for flat FRW, space is filled with particles. Space is filled with particles out to the asymptotic boundaries. That's the assumption of homogeneity, of course. And as far as we can tell, space is homogeneous. And that means that there will be fluctuations. For example, I'm not talking about CMB fluctuations now. It may include those. But in general, there will be fluctuations due to fluctuations in the matter, fluctuations in the temperature, it's not fluctuations in whatever, just fluctuations in the positions of particles. There will be fluctuations not only in the ordinary things, but even in the geometry of the boundary. The geometry of the boundary will also fluctuate. And that means that in cosmology, we are not working in some fixed, frozen boundary with some fixed, frozen background, excuse me. That, I think, is the primary reason why we as string theorists, I don't know if you're a string theorist, I don't even like the term string theorists, but we have had no real success in finding a framework for cosmology in the context of string theory. What I'm going to do is try to show you a possible framework. And the possible framework is based on the study of a cosmology within a bubble, within a nucleated bubble, and to try to understand how to describe it holographically and in a way that might be susceptible to string theoretic description and so forth. But for today, I'm not even going to talk very much about string theory. All right, the basic working tool of studying the creation of a nucleated bubble is instantons, Coleman-de Luce instantons. Coleman-de Luce instantons are Euclidean geometries which have the topology of a four-sphere. The Euclidean geometries and Euclidean solutions of equations of motion, including maybe some scalar fields and so forth. And they have the topology of a four-sphere, but a deformed four-sphere, which instead of having O5 symmetry, four-sphere would have O5 symmetry, they have only O4 symmetry. And the simplest example would be called the thin wall approximation, where you connect a de Sitter vacuum. The Euclidean description of a de Sitter vacuum is a sphere. You connect it to a completely flat vacuum on this side. This would be the Coleman-de Luce instanton for a transition from a de Sitter vacuum to a completely flat vacuum. Right. Slicing it through the middle corresponds to t equals 0, or corresponds to the symmetry point in the Coleman-de Luce instanton. And if you then go and try to make the Minkowski continuation of this, you do it as follows. You take the surface, the symmetry surface here, and you simply draw it over here. Starting at this end corresponds to starting at this pole of the sphere, and going around to here, to the pole at the center over here, corresponds to this point over here. So this surface is fully identical exactly as a space-like surface to what you would see if you sliced the CDL instanton right through the center. But then instead of evolving it away from here with the Euclidean equations of motion, you evolve it with the Minkowski equations of motion. What happens is you create a figure that looks something like this, with flat space in here in the dark regions, flat space-time in here in the dark region. I'll just remind you, full flat space, this entire triangle would be dark. But instead, it is now filled in here with de Sitter space. If you like, this is the nucleation point of a bubble. Only half of this diagram is really relevant to the bubble nucleation. You can forget the other half. The top half is relevant. And this figure in here is the nucleated bubble that took place in the background of the de Sitter space. The symmetry group O4 becomes O31 under the continuation. What is O31? Well, we'll come to what O31 is. But O31 is a non-compact group whose orbits move you around in the space-time. They're space-like in the bubble, space-like also in this bubble, time-like in this part of the geometry, in this diamond, and also space-like out here near the end of the de Sitter era. All right. But we're going to be mainly in here, and so you can see that the space-like orbits of the symmetry group really stand for nothing but translation symmetry. Well, not exactly translation symmetry, because the space in here is not flat space. We'll see what it is in a moment. But it's basically the translation of space inside the bubble. The intersection over here, where the future of the bubble intersects the de Sitter region, I'm just going to call sigma. But you can see what it means. From somebody inside the bubble, they're just looking out to space-like infinity. Space-like infinity. We'll come back to this geometry in a moment. Yeah. What the bubble is?
Yeah, so it's a nucleated.
Bubble of zero cosmological barrier constant in a de Sitter space.
Okay.
In the metastable de Sitter space. Right. Now, it's kind of interesting. The physics inside this bubble is not a finite universe. You would think it would be, because after all, you're inside a bubble. But in fact, it's an infinite, negatively curved FRW geometry. K equals -1. Negative curved and infinite. Why is that? Well, if you draw the space-like hypersurfaces that correspond to fixed, for example, if there was a scalar field which nucleated this transition here, then these would be surfaces of homogeneous scalar field. Those space-like surfaces, in fact, they are the space-like surfaces on which the symmetry group acts. Those space-like surfaces are infinite, and the reason is very simple. The metric diverges up in these corners here. In fact, the metric diverges all along here. The metric in these conformal diagrams is squished, it diverges in here, and the result is that these space-like surfaces are infinite, they're homogeneous, and they are hyperbolic planes, which means spaces of uniform negative curvature. Here's the metric. I'll ask you to get the, well, you won't have to memorize the metric, but I'll just show it to you. It's just ordinary FRW, the t squared plus a of t squared. And this metric here is the metric of space. It's the metric of a hyperbolic geometry. You would tell it's hyperbolic because of the sinh here. If it was flat space, it would just be r squared, but uniform negative curvature as a sinh squared. So the volume element increases rapidly. This is just a two-sphere, and roughly speaking, it corresponds to the two-sphere of the sky. When the observer at the center looks around, this is the two-sphere that he sees around him. Okay. So this is the metric that I'll be interested in. And over here, I've rewritten it, trivially, by replacing the time variable by conformal time. That simply means that you replace little t by big T such that little bt squared is a of t squared times big T squared. Standard operation. And if you do so, then the coefficient of the dt squared and the dr squared will be the same. And then you can work in terms of t plus r and t minus r. Those are kind of light cone coordinates. T plus increases as you move outward, away from the central observer here. And T minus varies along, basically along this surface here. That's what T plus and T minus are. Just keep them in mind because I'll use them extensively.
Can I ask one more question?
Yeah.
Sorry the really basic ones, but is this metric that you're describing here, is this in the dark region of that diagram, or is it in a bigger region? Do you remember the diagram?
No, yeah.
Where
No,
is
this is only, this is in the bubble, in the green region.
Yeah, but in a previous diagram, you had a dark region and a. I'm trying to connect this picture to the previous one.
Wait, going the wrong direction. Gave away my
There's one
place.
right there. So on
Yeah.
the right.
Yeah. It's the metric in here, in this diamond.
Oh, okay. All right.
In that diamond.
Okay, great.
Okay? Right. Bounded by a light cone in the past and bounded by a light cone in the future.
Can I also ask a question? You showed a special way to foliate this space with slices, which are there other foliations with something like flat curvature?
No, negative curvature.
So, okay.
Negative curvature. Negative curvature.
And that's the only way you can really foliate this space.
Yeah, it's pretty much the only sensible way. In particular, if there were a scalar field driving all of this, then the scalar field would be uniform on those surfaces. If there were particles produced, and in general there would be particles produced, temperatures and energy densities would be uniform along those surfaces. And there is a symmetry taking you from point to point with those surfaces. Okay, let me just tell you one or two remarks about the scale factor. If the cosmological constant is 0 at late times, then the scale factor at both early and late times simply varies as t itself, small t, that you can work out very easily. And it implies that the same A, but now the argument is conformal time. Conformal time, A goes as the exponential of t. Now, that further simplifies the metric, particularly if you go to late time and large r. Remember what r is? R is co-moving distance, coordinate distance out to a certain spatial point, out to a certain spatial distance. Here's what the metric looks like. Remember there was the dt squared minus the r squared. multiplying the scale factor here, dt squared minus dr squared just becomes dt plus dt minus. Okay? And then, let me go back a step. Okay, notice what was here. There was the dt plus dt minus times a of t squared. Okay, a of t is exponential e to the t. But then, for large r, sinh r squared becomes e to the 2r. So we get e to the 2t from here, e to the 2r from here, and the net result is that the coefficient of the two-sphere metric is e to the 2t plus. All right? It varies as you move out along the t plus direction. Now, let me come to what the census taker means. The census taker was originally introduced as an idea basically by Steve Schenker in an unpublished article, which has never been published and never will be published. But it's essentially, at least the terminology is certainly due to Steve Schenker. I won't take responsibility for it. But the basic idea had to do with looking back. We're going to come back, I hope, if we have time, to bubble collisions. These are other bubbles that form, and they're bubbles which are not disconnected from our bubble, but actually collide with it. We'll come back to why such bubbles inevitably occur. But taking the census simply means counting these other bubbles. It's a way of looking into the multiverse. It's a way of looking into the landscape and asking what other kinds of bubbles can there be besides our bubble. Anything which can be nucleated will be nucleated eventually, as we'll see. And so the expectation is that anything on the landscape can be nucleated in this manner, and therefore can eventually be seen by an observer moving up toward the tip of the light cone here, or the tip or time like infinity. There can be many census takers. One over here, one over here. They all move up to the tip of the light cone, and we call the tip of the light cone the census bureau, the place where the census takers come and compare notes. Okay, so the census taker is just some observer who looks back from progressively later and later times, and notice that at an early time, he sees none of these bubble collisions. As time goes on, he sees the earliest bubble collision, the earliest nucleated second bubble. As time goes on, he sees more and more of the late-time nucleated bubbles, and in fact, they look smaller and smaller on his sky. That's the picture you should have. As the census taker moves forward in time, he can see back and see smaller and smaller structure on the sky, the smaller and smaller structure corresponding to later and later bubble nucleations. That's the picture. Now, there's going to be some reasons why this would be exceedingly hard to see in the real world, but in principle, all of this can be seen. Let me summarize the geometry. Here's the FRW patch. It's parameterized, first of all, sigma, remember, that's asymptotic in space like infinity. It can also be thought of as the intersection of the generators of the asymptotic light cone with the bulk of the geometry. At this point, the generators go into the bulk. It is just the surface, the two-sphere at infinity. And then, in addition to the coordinates of sigma, we would also have the coordinates t plus, which runs out, and t minus, which runs along the generators of the patch. Now let's think about the census taker for a minute. Here's the census taker again. Think of the backward light cone of the census taker, what the census taker can see in his backward light cone. That light cone is a surface of fixed t plus. All right? Assuming the census taker is right at r equals 0, then as far as the census taker goes, he is a surface of constant t plus, or he looks back and sees a surface of constant t plus. So we can identify the time of the census taker as he moves up here with t plus. Good, that's interesting. Now, let's think of a space-like surface that the census taker looks back and sees, some particular one. It could be any one. They're all the same, or that is to say, they all have the same geometry modulo the scale factor. let's think about what the census tab, well, let's first of all think about what those space-like surfaces are like. Those space-like surfaces are hyperbolic planes. I always include this picture in every seminar I ever get because I love it so much. I do believe that Escher made a bargain with the devil to be able to create an infinite number of them near the boundary here. I can just see him working with his little pen. But this is a picture of the hyperbolic plane. This is two-dimensional, of course. We're talking about 3 dimensions. And each angel and devil is, of course, of the same size, intrinsic size, proper size. And there is a symmetry which moves you around from devil to devil. That symmetry is, of course, translation symmetry, or the analog of translation symmetry on the uniformly negatively curved surface. It's the 031 symmetry. The symmetry which moves you around and slides you around and takes one devil to a neighboring and so forth is exactly the 031 symmetry. This geometry has another name. Now not thought of as a sequence of different time slices, but just at a particular time slice. The negatively curved geometry like that also goes under the name of Euclidean anti-de Sitter space. Euclidean anti-de Sitter space is exactly the same space as a space-like surface of negatively curved FRW. Let me just give you a quick review and a tiny, tiny bit of information about the connection between anti-de Sitter space and boundary quantum field theory. This, of course, is the holographic principle coming into play. The holographic principle says that the physics of anti-de Sitter space, the interior, the angels and devils, are exactly equivalent to a conformal field theory that lives on the boundary. So it's the holographic correspondence, if you like. How, from the point of view of the field theory, do we understand the radial direction? Radial direction, on the one hand, can be mapped into size scale in the boundary quantum field theory. The boundary quantum field theory is a conformal field theory. It's scale invariant. If you have an object on the boundary, you can make it smaller, you can make it bigger. The bigger the object, the more it corresponds to something near the center. The smaller it is, the more it corresponds to something near the boundary. Another way of saying it is that the radial direction corresponds to renormalization group flow. Sorry, Laurent. No objection from Laurent? Maybe he's not here. Laurent here? No. Good. Excellent. No, there's no real objection. It's just that this correspondence is a fuzzy correspondence, and it's fuzzy to within about 1 ADS radius. You wouldn't want to push it too hard at small distances. But roughly speaking, on a scale of the ADS radius, which means about the size of one devil here, this is a correct correspondence. Renormalization group flow. Motion in and out is renormalization group flow. What I have here in mind for kappa is, of course, the renormalization energy scale. So the further you go out, the smaller the distance scales of these angels and devils, but also the higher the corresponding momentum scale in the dual conformal field theory. So I want you to remember that. Radial motion is renormalization group flow. And the other thing I've written down here just for future reference is the form of a correlator of a scalar field of dimension delta. Right? In the boundary conformal field theory, well, this is the structure that it has. 1 minus cosine alpha. Cosine alpha is the angle, or alpha is the angle between 2 points on the boundary, or in the boundary conformal field theory. Represents the separation between points. 1 minus cosine alpha goes to 0 when the points come together, to the minus delta. That's the typical conformal correlator. Dictated. Oh, where did conformal invariance come from? I'm sorry, I didn't even mention conformal invariance. The important point is that the symmetry group of this space, when it acts on the boundary, generates conformal transformations. Okay? So this is the typical form of conformal correlator. In fact, these factors here are really there in correlation functions. These are wave function renormalization constants. Wave function renormalization constants scale with the cutoff momentum to the power delta. They're really there in the correlation functions. We usually strip them off and define the correlation function or define the fields in such a way we renormalize the field by multiplying by k to the delta as we take the cutoff momentum larger and larger, and then strip them off and throw them away and say that the conformal field theory correlators is this. But they're really there even in the field theory. We can also understand them in another way. If r is log k, then k is e to the r. So this represents e to the minus delta r. What's going on is if we think of the correlators in the bulk, and then imagine sliding them out to the boundary, they fall like e to the power minus r delta for each external line. And in fact, so the correspondence between bulk and boundary is very close. Wave function renormalizations just become the behavior of fields as you move toward the boundary. Okay, now let's come back to cosmology. The census taker looks back, and as he looks back at later and later time, his backward light cone moves out toward the boundaries of space. Okay, remember that t plus is the census taker time, but we could draw that as follows, or we can think of it as follows. As the census taker time evolves, his backward light cone expands out and moves out closer and closer to the boundary. The point is that to the extent that there are interesting correlations on the sky, first of all, because of the symmetry, the correlations on the asymptotic sky should be organized according to conformal representations. Why? Because they're conformally symmetric due to the symmetry which manifests itself as conformal symmetry. So first of all, the observer will organize his measurements and will organize his observations according to conformal symmetry. But as time goes on and this surface moves out and out and out, it's quite clear that it's generating a renormalization group flow. As time goes on, the observer sees smaller and smaller structure on the sky, right, and sees finer and finer detail on the sky, and it is clearly generating some kind of renormalization group flow in some kind of structure which has conformal invariance. Now, what is that structure on the sky? Is it a conformal field theory? And incidentally, since this surface is a space-like surface, causally it's a space-like surface, then this will have to be a two-dimensional, because the sky is two-dimensional, Euclidean conformal field theory. This is just a two-dimensional spatial surface from the point of view of the causal structure of it. Well, how do we find out what kind of structure it is? The best way that I know is to start thinking about correlation functions of bulk fields on the boundary. This is the same thing that we would do in anti-de Sitter space. And the way to calculate them is to start with the Coleman-de Luce bubble, calculate correlation functions. It's not so easy. I mean, I'm making it sound easy. It's rather hard, but doable. Calculate correlation functions, put the points into the flat space region, analytically continue from the Coleman-de Luce instanton to the Minkowski signature geometry, and then slide the points back or push the points back to the boundary. Right? This is very similar to what we would do in anti-de Sitter space, except there's an extra dimension. There's a time dimension in addition to the dimension in the surface. Question. Is there a dual Euclidean two-dimensional conformal field theory on sigma? And if there is, how do we understand the extra dimension of time? All right, I'm going to, oh boy, do I really want to go through this? Yes, I'm going to go through it. You're hostage to me now because the doors have just been locked and you cannot get out. I'm going to tell you what the correlation... Lock the door, please. Would you mind locking the door? How much time have I gone already? My God, let me tell you what's here. These are calculations of the correlation functions for tensor and scalar fields. Tensor meaning the gravitational fluctuations, scalar meaning minimally coupled scalar. Minimally coupled scalar, massless. I'm going to just briefly tell you, there are two kinds of contributions to the correlation function. And I have names for them. I used to call them proactive and reactive. It was stupid names. My wife made them up knowing nothing whatever about physics. I just asked her, give me two words. And she said proactive and but I realized later that I'm really talking about renormalization group covariant and renormalization group invariant operators, or invariant correlation functions. And I'll tell you what that means as we go along. But in any case, here's what follows. First of all, you can see the structure of these correlation functions have some prefactors in front of them that depend on the times and radial distances, the t pluses and the t minuses of the external points. All right. When you pull them back to the surface sigma, t plus and t minus asymptotically go to some values. All right. But each one of them, each term in the expansion, is a conformal field theory correlator. And they're discrete. That's a surprise that they're discrete. It's not obvious that they should be a discrete collection of them. They're discrete, they have integer dimension, and they begin at dimension 2. And notice that this term has a trivial dependence on t plus. In other words, as you move out toward the boundary, every term in it has exactly the same t plus behavior. But the interesting dependence is on t minus, and that contains the dimension of a field. And the form of it, there's a constant times e to the something involving delta times t minus as you move along here, times 1 minus cosine alpha to the delta. So we see a collection of conformal correlators. But the main thing about it is that it depends on t minus in a certain way. Then there's another collection of terms. Where they came from is not so important right now. The structure is important. And the other term, which I call the renormalization group invariant, depend only on t plus. Don't depend on t minus at all. In the case of the tensor correlations, there's a term here. How do we understand that term? That term can be understood as zero dimension, as a zero dimension operator. Logarithmic divergences instead of power law divergences are what you expect for dimension 0 operators. So first of all, there's a dimension 0 operator, which I will identify in a little while as a Leoville field on the boundary, on the asymptotic boundary. And then there's a collection of things which just depend on t plus with the prefactors e to the minus delta t plus times the same kind of conformal correlators that appear here. Seem to be two kinds of objects. And the interesting question is, what do those two kinds of things correspond to? What are they? From the point of view of the potential hypothetical boundary field theory, what are these two things? Well, let me come back for a minute. What does this piece tell you? This piece is only there for the tensor correlator. For the tensor correlator, there's this zero dimension piece, and I called it Leoville. If you look at it, this term is pure gauge. Don't worry about it. It's just pure gauge. It's trivial. Right? Take it from me. Believe me. This is the interesting piece here, and it doesn't depend on radial distance. It's just fluctuations in the geometry which extend out to infinity. In other words, it is not like anti-de Sitter space where the fluctuations in geometry are frozen at infinity and go to 0, but rather there are fluctuations in the geometry which extend out to infinity with constant coefficients, which means, in effect, that the geometry at infinity, asymptotic geometry of the surface at infinity, is not round. It's got a geometric texture to it, and that geometric texture is dynamical in the same sense that all the other fields are dynamical. It's actually frozen with time, no time dependence in it, but it has some statistical distribution. Roughly speaking, what it says is that the asymptotic geometry is lumpy. Lumpy and has multipole moments of all kinds. Why is this? This is the effect of the asymptotic warmness, of the non-asymptotic coldness of cosmology. And that's the difference between anti-de Sitter space, that the asymptotic behavior is not frozen in the same way. What does it manifest itself in? It manifests itself in a Leoville field. A Leoville field, we're going to go through what Leoville fields are and how they work. Yeah, we still have a few minutes. But let me just, for the experts, let me just point out where another way of thinking about this Leoville field. The S squared, this is the area element of a two-sphere, namely the two-sphere which is represented by this green line. The green line is not at the boundary, it's at some r and at some time in general. That looked like A of t squared times sinh squared r times d2 omega squared, or A of t squared times e to the 2r, e to the 2r because the sinh asymptotically is just e to the 2r. I'm going to give this a name. I'm going to call this the reference metric, this piece over here. And that would be there, incidentally, in anti-de Sitter space. The new thing is this time dependence here. Well, if the geometry is asymptotically warm, that means that there are not well-defined frozen clocks at infinity that keep track of time in a way which is appropriate, for example, for an ADM description. Time, everything fluctuates out in infinity, and it doesn't make any good sense to say time. You have to think of time as a local thing. The time over here, the time over there, and so forth. Or another way of saying it is the formalism should be invariant under transformations under shifts. But I'm only talking pretty much about shifts far away now, asymptotically, because that's where I'm concentrating. T goes to T plus some f of omega 2. The formalism should be invariant on that, under that, because there is no preferred time in asymptotically warm geometry. That means that this ds squared is really going to have, instead of just the reference metric times e to the global time, it's going to have something which depends typically on position on the sky, e to the u omega of omega 2. This is what is called a Leoville field, a metric which depends on a reference metric times a field which varies over the sphere, over the geometry. Now, is this dynamical? Yes, it is dynamical. In order to make the formalism gauge invariant, you have to integrate over these shift functions, or these laps. I guess this is a lapse function. You have to integrate over them, very similar to what you would do in the Wheeler-DeWitt formalism. And this e to the omega 2 really does become a dynamical field. It's a Leoville field. For experts, it happens to be a time-like Leoville field, which means its kinetic term is negative. We can come back to that, why that's so. So the main point and the main lesson now is that in addition to the degrees of freedom that you would have in a anti-de Sitter space, you have additional degrees of freedom associated with the geometry of the boundary, which don't go to zero. And they correspond to zero-dimension fields, which would not be present in anti-de Sitter space. But otherwise, it's very similar. OK, so let me go on and tell you just a little bit about how the renormalization group flow works. I will not get to the end of the seminar. I never get to the end of my seminars. But let me tell you a little bit about how the renormalization group of Leoville theories work and how it's connected to the origin of time and to the space-time that it's trying to describe. Leoville is a trick for summing over surfaces. All the people who study two-dimensional quantum gravity are extremely familiar with it. And one of the ways of summing over surfaces is to triangulate them with fishnet diagrams. You triangulate them, and instead of summing over the metric, you simply sum over the structure, the triangulation itself. Everybody who does quantum gravity by triangulation will recognize what I'm talking about. And we can think of this fishnet as actually defining a true metric. We want to sum over it. Well, we're trying to do something which is beyond the normal rules of quantum field theory. we're trying to do a path integral over geometries, offhand, we don't really know how to do that. And so the experts who do this kind of thing and try to do it by using standard quantum field theory do the following trick. They introduce a reference lattice or a reference metric. You can always think of a metric as a kind of lattice. They introduce a reference metric, the only rule being that the lattice spacing on the metric, on the reference metric, should be a lot larger than the lattice spacing of the true metric. And the reference metric is kept absolutely fixed. It corresponds to a lattice, for example, a definite lattice on the sphere of the sky. We're not going to vary it. It's arbitrary but fixed. Arbitrary but fixed, a reference metric. And then we integrate over all the degrees of freedom as this fishnet moves around. Incidentally, the fishnet can also have, of its vertices, other kinds of degrees of freedom, icing degrees of freedom, all kinds of things. We integrate over them and define effective fields, either at the vertices or in the triangles. It doesn't matter very much. We define effective, renormalized, averaged fields. The condensed matter physicists would call them block spin fields or whatever we like, on this fixed lattice. Integrate over them, and that defines a quantum field theory on the fixed lattice. That's the idea of Leoville theory. That's what Leoville theory does. Now, the definition of the Leoville field is simply the relationship between the true metric and the reference metric. Whatever reference metric you pick, the true metric is related by e to the u times the reference metric. Let me just go back a step and point out the similarity with this formula here, and also remind you that this u is simply local time. Okay, local time near the boundary. So Leoville does have a structural similarity to what we're doing, but what I want to talk about for just a very short brief time is the renormalization group structure of a Leoville theory. Well, first let me remind you about renormalization group structure in ordinary field theory. This is what I call the Wilson line. The Wilson line simply means the line of scales, starting at the infrared. And the infrared could correspond in QCD, it could correspond to the confinement scale. In our problem, it corresponds to the size of the sphere that we're doing our field theory. That's the coordinate size of the sphere in our problem. It's an infinite axis if it's a continuum field theory. But we pick a point which we call either the renormalization point. I'm inclined to call it the reference point. Again, it's just a reference lattice, if you like, in the field theory. And we integrate out all the degrees of freedom on scales shorter than the reference scale. That defines for us an effective action at reference scale R. That's basic. That's in a nutshell. That's renormalization group. Okay. Renormalization group refers to the variation of this L of R as you move this point around. Right. What's the difference with Leoville theory? With Leoville theory, you actually have two scales. You have this fishnet scale. It's a local scale. It varies from place to place, but you can think of it as the bare lattice spacing in the theory. Right. It is to be integrated over. It's not something which you choose. It's to be integrated over. But let's suppose that it fluctuates about some mean. So put it out here. That's the fishnet scale on the one hand. And then there's the reference lattice scale over here. So there are 2 degrees of freedom. The Leoville field is the ratio of these 2 scales. And logarithmically, the Leoville field is simply the distance from here to here. Okay. But we also identified the Leoville field with local time. So here you see the origin of a new time scale, which did not appear here. This could have been ADS CFT, and this R variable is just the R coordinate of the ADS, the radial coordinate, and it is the renormalization group scale. Here we have another scale. The other scale is the distance logarithmically between the arbitrary but definite reference scale and the true short distance ultraviolet scale of the theory, which, as I said, we do integrate over. Notice in both, well, in this case here in particular, that we would tend to a continuum limit by going to large T. A continuum limit means that we take the lattice spacing here smaller and smaller, and to get to that, that corresponds to increasing time. So very late times correspond to the continuum limit of this Leoville theory. I'm going to assume that the continuum limit is at a fixed point, just for fun. It doesn't have to be at a fixed point, but is at a fixed point of the renormalization group. What that means is that you integrate out, as T gets larger and larger, you integrate out more and more degrees of freedom and eventually run to a fixed point. That's my assumption. It will run to a fixed point of the renormalization group. So fixed point physics and continuum physics would correspond to very late time physics. And that's a theme throughout here, that the endpoint of a renormalization group flow at a fixed point corresponds to asymptotically late times. I recognize that people are going to have trouble following this, but you have to see it a few times before you get it. In my own opinion, it is rather important. So let me continue. Now let me explain to you these two objects that appear in the correlation functions. You know what? I don't know whether to stop, let people out of here. What should we do? It's an hour gone by. And I am not finished. And I can stop right here and, yeah, continue for those who wanted, we can do. Or we can. Yeah, the 5-minute summary is that the renormalization group flow corresponds to the observations of the census taker as time gets later and later, looking out further and further into the sky. And quantum field theory is the organizing principle to organize those observations. That's the bottom line. And much about the structure of the sky. Now remember, we're talking about zero cosmological constant, so there's caveats here. But much about the structure of a very deep sky, way, way beyond the surface of last scattering, that you can only see by gravitational waves, much about the structure of the sky is organized and determined by the dimensions of operators in this conformal field theory. The way, in particular, the time evolution that the census taker would see of the sky is determined by the dimensions of operators, and so I don't know what to do. We can. I'm happy to continue. I'm also happy to stop.
I'm going to say that you can continue discussing with people who are interested.
Yeah, I think so.
Geez, but why don't we Frank Lenny first talk?
Yeah.